The precision of ancient optics did not begin with the glass lenses of the Renaissance. It peaked more than 2,000 years earlier in the dry, dust-choked workshops of early Mediterranean craftsmen working with pure crystalline quartz. Standard archeological narratives tell us that the ability to correct human vision, magnify microscopic details, and focus solar energy into high-intensity thermal beams was a modern breakthrough. That is false. The physical reality of the Nimrud lens, a 3,000-year-old oval of natural rock crystal recovered from the Assyrian palace of Nimrud, shatters this timeline completely. This artifact was not a decorative bead or a crude piece of jewelry. Optical testing reveals it possesses a distinct focal length of approximately 12 centimeters, functioning as a deliberate, low-power magnifying glass capable of concentrating sunlight. But the Nimrud lens is merely the crude surface of a far more sophisticated, decentralized network of ancient optical engineering that stretched from the master stone carvers of Minoan Crete to the high-tech industrial workshops of classical Greece and Rome. To understand how these ancient lapidaries achieved this, we have to look past the stone itself and examine the microscopic physics of abrasive mechanics. The manufacturing process did not rely on metal files or iron blades, which are far too soft to cut through quartz crystal. Instead, ancient engineers exploited a fundamental principle of material science known as abrasive slurry kinetics. Rock crystal has a Mohs hardness rating of 7. To shape it, craftsmen utilized an ultrafine slurry of emery, a naturally occurring rock rich in corundum, which boasts a Mohs hardness of 9. By suspending this crushed emery powder in olive oil or water and pressing it against the quartz using a rotating copper mandrel, they initiated a process of microfracturing at the molecular level. The copper mandrel did not do the cutting. It merely acted as a soft matrix that captured the microscopic emery particles, holding them in place as they ground away the crystalline structure of the quartz. This technique allowed for the removal of material with nanometer-level control, bypassing the natural cleavage planes of the crystal that would otherwise cause it to shatter under direct impact. The sheer physical stamina and spatial awareness required to maintain a perfect, consistent curvature across a brittle, non-homogeneous surface without the aid of automated lathes represents a pinnacle of forgotten mechanical intuition. This mastery of material removal becomes terrifyingly precise when examining the Minoan seal stones found in the Aegean basin, dating back to 1500 BC. These miniature masterpieces, often no larger than a fingernail, feature intricate, deeply carved anatomical details of warriors and deities that are completely invisible to the naked human eye. When viewed under modern scanning electron microscopes, these carvings reveal a total absence of tool chatter or irregular deviations. The lines are smooth, continuous, and cut to uniform depths of less than a millimeter. Biomechanical experts have demonstrated that the human eye cannot physically focus sharply enough at the close distances required to carve these stones without optical assistance. The craftsmen must have used magnifying lenses. This implies that the production of lenses was not an accidental byproduct of gem cutting, but a deliberate, parallel technology developed specifically to enable the creation of high-density microart. They created the tools to see the world smaller, which in turn allowed them to compress information onto stone with a density that defies the limits of unassisted human biology. The optical geometry of these early crystals was not limited to simple magnification. It extended into the deliberate manipulation of light polarization for maritime navigation. Centuries before the invention of the magnetic compass, seafaring civilizations utilized what are known as sunstones, typically composed of Iceland spar or natural cordierite. These crystals possess a unique optical property called birefringence, meaning they split an incoming beam of light into two separate rays polarized at right angles to each other. When a navigator looks through a properly oriented birefringent crystal at the sky, even on a completely overcast day or when the sun has dipped below the horizon, the crystal changes color or intensity based on the alignment of the sun's hidden rays. By rotating the stone until both split images reach equal brightness, the navigator can pinpoint the exact position of the sun within a fraction of a degree. This was not mysticism. It was an empirical utilization of atmospheric Rayleigh scattering, transforming a raw geological anomaly into a precise, solid-state navigational computer that mapped the geometry of the upper atmosphere to guide wooden hulls across featureless oceans. As this optical expertise migrated into the classical Roman world, the medium shifted from natural quartz to synthetic materials, triggering the birth of structural glass blowing and specialized glass chemistry. The Romans discovered that by adding precise ratios of antimony oxide or manganese dioxide to their molten silica mixes, they could neutralize the green tint caused by iron impurities naturally present in sand. This resulted in vitrum, a remarkably clear, colorless glass that allowed for the mass production of cast and blown window panes, and crucially, water-filled glass spheres known as burning glasses. Roman naturalists recorded that these water-filled globes could intensify ordinary ambient sunlight to such an extent that they could instantly char wood or cauterize medical incisions. This represents a critical bridge between ancient material science and thermodynamic engineering. The Romans were not just looking through glass. They were using the geometric properties of fluid refraction to concentrate diffuse atmospheric energy into localized, high-temperature focal points, effectively weaponizing the refraction index of water. This brings us to the most controversial and misunderstood pinnacle of ancient optical engineering: the legendary solar burning mirrors deployed during the siege of Syracuse. While popular history often dismisses the accounts of Archimedes using mirrors to ignite the Roman fleet as a mathematical impossibility, an examination of catoptric geometry reveals a different reality. Archimedes did not use a single, massive, impossibly large curved mirror. He understood that a parabolic surface is difficult to manufacture at scale, but can be perfectly simulated using an array of flat, highly polished bronze mirrors tracking a single target in unison. This is the exact principle behind modern heliostat arrays used in solar thermal power plants today. By coordinating dozens of soldiers, each holding a flat bronze shield polished to a mirror finish, and directing their individual reflections to converge on a single localized area of a wooden hull. The cumulative thermal energy would easily surpass the auto-ignition temperature of dry pitched wood. It was an exercise in distributed computational geometry, using human operators as the actuators of a massive, living parabolic concentrator. To fully grasp how these ancient optical achievements tie into modern technology, we must look at the field of modern lithography and semiconductor manufacturing. The fundamental challenge of modern chip making is the projection of incredibly complex geometric patterns onto silicon wafers using light, passed through highly specialized, flawless reduction lenses. When we strip away the automated cleanrooms and digital control systems, the core physics of modern photolithography, refraction indices, wave interference, and precise focal alignment remains completely identical to the principles exploited by the Minoan lapidaries and Roman glassmakers. The ancients achieved through sheer tactile feedback, empirical observation, and generational refinement what we achieve today through laser interferometer control loops. They were mapping the behavior of photons using raw earth, oil, and human muscle, proving that high technology is not defined by electricity, but by the precise, systematic manipulation of the laws of physics. The transition from raw crystal carving to predictable optical instruments required a profound understanding of geometric refraction centuries before Willebrord Snell formulated his mathematical law. Ancient engineers observed that light bent when passing from air into water or glass, and they systematically exploited this boundary behavior. In the ancient libraries of Alexandria, scholars compiled extensive tables detailing the angles of incidence versus the angles of refraction for various media. They discovered that by altering the curvature of a polished surface, they could predictably alter the trajectory of incoming light waves. This allowed them to construct specialized lenses designed for distinct tasks: flat convex lenses for intense magnification of legal documents, and double convex lenses designed to project small, inverted images onto flat surfaces. This knowledge was preserved within tightly guarded guild secrets, passed down through lineages of master glass blowers and stone cutters who treated the refraction of light not as an abstract academic exercise, but as a practical industrial tool. This industrial application of optics is vividly demonstrated in the ancient production of imitation gemstones and complex mosaic glass work, such as the famous Lycurgus cup. This 4th century Roman glass chalice exhibits dichroic properties, meaning it changes color from green to red depending on whether light is shining through it or reflecting off it. Modern materials scientists analyzing fragments of this glass discovered that the effect was achieved by infusing the molten silica with a precise colloidal suspension of silver and gold nanoparticles, ground down to an astonishing 70 nanometers in diameter. The Romans had accidentally or empirically mastered nanotechnology. They understood that by manipulating the particulate composition of matter at a scale far below the wavelength of visible light, they could completely alter the material's macroscopic optical properties. This chalice was not a simple decorative cup. It was a highly sophisticated light-filtering device that utilized localized surface plasmon resonance to manipulate photon scattering. a technology that modern laboratories are only now fully exploiting for advanced biosensing and optical computing. The precision required to create such nanomaterials points to an environment where temperature control and chemical purity were managed with rigorous, repeatable accuracy. Roman glass furnaces were engineered to maintain steady temperatures exceeding 1,000 degrees Celsius for days on end, utilizing specific wood types to avoid introducing contaminating ash into the crucibles. They designed multi-chambered kilns that separated the combustion zone from the melting pot, preventing direct contact between the fuel gases and the glass batch. This level of thermal isolation was vital for maintaining the delicate chemical equilibrium required for clear glass and dichroic effects. It shows that ancient optical engineering was not the result of isolated strokes of genius by lone inventors, but the product of a highly developed, interconnected chemical and thermodynamic manufacturing ecosystem that spanned the entire Mediterranean basin. When we look closely at the architectural layout of ancient sanctuaries and temples, we find this optical expertise applied on a monumental scale. Architects did not just build walls, they engineered large-scale solar alignment systems that utilized the natural optics of the atmosphere. By positioning narrow apertures, polished stone reflective surfaces, and dark interior chambers with mathematical precision, they could capture the first rays of the solstice sun and project a highly focused beam of light deep into the innermost sanctums to illuminate specific statues. This was a physical implementation of a camera obscura on a civic scale. The entire building functioned as a giant optical instrument, using the Earth's precise orbital mechanics as the light source and the stone architecture as the aperture and projection screen. This requires a level of geodetic surveying and astronomical calculation that rivals the precision needed to grind a magnifying lens. The economic infrastructure required to support this level of optical production was vast and highly specialized. The procurement of high-grade, inclusion-free quartz crystal required extensive mining operations in remote regions like the Alps and the deserts of Madagascar and India. Once extracted, these raw crystals were transported along dedicated trade routes to urban centers where specialized lapidary guilds possessed the proprietary knowledge needed to cut and polish them. These guilds operated under strict quality controls, using standardized testing methods to ensure the uniformity of their optical products. The high value placed on these lenses and crystals in ancient trade registries indicates that they were viewed not as luxury novelties, but as vital industrial components essential for state-level administration, high-end manufacturing, and military signaling networks. The military application of optics extended far beyond the defensive burning arrays of Archimedes. Long-distance communication across ancient empires relied heavily on heliotrope signaling networks, which used highly polished metallic mirrors to flash coded messages across vast distances. Roman military treatises describe a system of watchtowers positioned at strategic intervals across the frontiers, each equipped with signaling mirrors capable of transmitting tactical data across tens of miles in a matter of minutes. This ancient optical telegraph system required an understanding of line-of-sight geometry atmospheric distortion, and curvature of the Earth corrections. A single operator manipulating a polished bronze surface to intercept and redirect sunlight could alter the movement of legions hundreds of miles away, demonstrating a structural reliance on optical data transmission that mirrors our modern fiber-optic telecommunications networks. This integration of optics into daily administrative and industrial life completely reframes our understanding of ancient technological capability. The boundary between ancient empirical craftsmanship and modern scientific methodology blurs when we analyze the physical artifacts left behind. The master stone carvers, the glass chemists, and the architects of antiquity were all operating within a unified framework of physical manipulation, treating light, heat, and matter as highly malleable inputs for complex engineering challenges. They did not need digital computers or automated machinery to achieve micro-precision. They replaced those systems with an unparalleled mastery of material properties, rigorous geometric calculation, and thousands of hours of highly disciplined human labor. The legacy of this ancient optical paradigm survives in the very structure of modern scientific inquiry. The foundational principles of geometry, refraction, and material manipulation that allow us to build space telescopes and manufacture microscopic computer chips were mapped out by individuals working with nothing more than sand, oil, copper, and stone. By stripping away the layers of historical bias that treat ancient peoples as primitive or reliant on mythological intervention, we uncover a world of profound mechanical sophistication. It was a world where light was not merely seen, but engineered, harvested, and transformed into a potent tool of human intent, leaving behind a legacy written in the flawless surfaces of ancient quartz and the enduring clarity of ancient glass.